Hi! So a couple weeks ago I made this video where I, as a pretty established competitive programmer with basically zero experience in interview stuff, took on a bunch of FANG questions to see how it would go. And it went pretty well. But I got quite a few comments about stuff like coding style and how it's really the thought process that matters and stuff like that. And yeah, those comments have a point. The previous video didn't really do those things justice, since my goal was just to finish the questions as fast as possible. So in this video, I'm doing a full-on mock interview, where I'll be making the effort to explain my thoughts throughout, and actually use a human-readable coding style. I'm gonna treat it like a real interview, but I've also had very little time to prepare, so we'll see how that goes, because my code is historically as bad as my handwriting. But also this will be more realistic, and probably more useful too. And before you ask, no, I didn't get Clement. Not yet, at least. Nope, this interview will just be between me and you. And yeah, that's why the thumbnail's in space, because there's nobody around. And you can argue that not having an interviewer makes it inauthentic, but really the only difference between having an interviewer and not is that there's no back and forth, no confirmation of ideas. But LeetCode gives me that anyway by telling me if my code is correct or not, so it's not such a big deal. And the other only difference is that there's nobody to grade my performance, except there is because there's you, or others in the comment section if you don't want to. So I picked 2 LeetCode mediums from a Google list and then got bored and did a hard, so 2 mediums and a hard. And if you want to follow along, the links are in the description. And yeah, we're doing multiple because I want watch time. After each question, I'll do a recap of how it went in my view after spending a bit of time reflecting on each one. Just a bit of extra content. And on another note, this video has honestly got something for everyone. Whether you want to learn from the thought process or watch some interview questions get destroyed or just even laugh at someone who has a bad style, this video's got you covered. So the question to be answered is, how much does competitive programming prepare you for this stuff? Is it a blessing that lets you blaze through questions that would normally be difficult, or is it a curse that forces a bad coding style upon you? Or both? Find out now. And if you like this format, definitely subscribe, because if this video gets me 2,500 subs, I'll do the same thing but for another FANG company to add a bit of diversity. So hit that button. That is all. I'll shut up now. Let's get started. Alright, so we have this question, fruit into baskets, and let's just start by reading it. So you're visiting a farm that has a single row of fruit trees arranged from left to right. The trees are represented by an integer array of fruits, where fruit's eye is the type of fruit the ith tree produces. You want to collect as much fruit as possible. So you only have 2 baskets, and each basket can hold a single type of fruit. Starting from any tree of your choice, you must pick exactly 1 fruit from every tree while moving to the right. The picked fruits must fit. Okay, so you have 2 baskets, so you get 2 types of fruit total. If you have more than 2, then it's impossible. Yeah, once you fit a tree with fruit that cannot fit, you must stop. Okay, yeah, so looking at this, it's 2 different types, basically. So when we have more than 3 types, it's not valid. Okay, so immediately, the most basic solution is to just write a brute force. So for example, here, when we have this, then we could try each L, and then for each L, we can iterate to the right, and then add in each fruit to our basket. So for example, say this was, let's say we start out here, so 1, 2, 3, 2, 2, 2. So we insert 1, like so. So we have 1, then we try here, we insert 2. Then there's still only 2 different types, so that's fine. Then we try here, we insert 3, now there are 3 different types, so that's invalid, and this is the best we can do. And then we try each starting point. And that's fine, but that kind of sucks, because that's O(n) squared. But this kind of smells like 2 pointers, because when we have, like, if this range, like if starting L here is valid up until this R, then this L, the L over here, is also going to be valid at least up to this R, since the only difference is that we took away this fruit, which means that it's easier to get to this R because now we have 1 less fruit to worry about. So this L is guaranteed to get to this R, and it can get even farther depending on the input. So basically, as L increases, as our L goes to the right, our R will also go to the right. So that means we can use 2 pointers on it. Right, so to use 2 pointers, what we need to do is we need to be able to check in O of 1, is this range valid? So what we can do is so essentially to check if a range is valid, let's say for example here, let's fill in the array elements again. Is it 2 3s or, yeah, 2 2. So what we can do is, basically we need like a list of the unique types in a range. Let's use a different color. So the unique types in a range. So for example here, the unique types are 3 and 2. So we can store, I guess we can store a map. If we store a map, well, we need to be able to we need to be able to maintain it. So we need to be able to easily insert an element. So say there's like a 5 over here, then we need to insert that quickly. And we also need to be able to delete elements since our range is going to move from the left to the right. So the easiest way to check if an element is no longer in the list, so for example, when we remove this 2, we still have a 2, but when we remove this 3, we don't have a 3 anymore, so we have to remove it. So probably the easiest way to do that is to keep a count of each element. So this can be like a mapping element and count. And then when we remove an element, if its count becomes 0, then we can remove it from the map, and if its count remains not 0, then we can keep it in the map. Okay, so we 2 pointers across, and then we keep track of it using a map. So overall, how much space do I have? So overall, 2 pointers. Okay, let me just reset the canvas. So we do 2 pointers. We can, for example, iterate over R. So we have R here, and then initially our L is over here, so we just have a single element, and that element is always going to be valid. Okay, now we move R over here. So let's say R is here now. So now our current range switches from this to this. So now what we do is we insert this element into the range, and then using our map, let's do some examples. So 1, 2, 3, 2, 2. So using our, I forgot what color I used. So using our map, when we move R over here, we insert this into the map. So now we have for example, we have 1 mapping to 1. Let's make that a bit wider. We have 1 mapping to, we have a single 1 and a single 2. So now this is still valid, so we can just keep moving R over. So we move R over here. Now we have 3 mapping to 1, and now it's invalid. So now what that means is we have to move L over. So L moves over here, and we remove the 1. And then in this case, we can just keep moving R over, and it stays valid. So that's the basic idea. We do 2 pointers on the array, and to check if a range, and then we keep moving R to the right. So we iterate over R. And then let's say for example our range is this. What we do is we use the map to quickly check whether we have at least 3 distinct elements in the range. And if so, or rather while so, we remove the leftmost element and we move the left pointer one to the right so that our new range becomes, for example, this. And then we would keep moving the L to the right until it's valid again. Yeah, this makes sense. Okay, so the easiest way to use a map in C++ would be the unordered map, which is of 1 in practice, especially since the map size is like always less than or equal to 3. So we don't really need that much. We're not going to use that much space. We're not going to use that much time. So unordered map should be fine. I think that's it. Are we done? I guess that's the algorithm. Okay, I guess we can code it. Alright, so the initial thing we need to do is initialize and answer the longest range. Then we can iterate over R as so. And then we initialize L to be 0. So now what we do is, at every point, whatever our current R is, we insert it into the range, because when we move R1 to the left, then our range becomes, for example, this. So we need to maintain an ordered map counts. So we keep count of each element. Counts fruits R plus plus, because now we insert R into the range, and then while this range is invalid, if this range is invalid, then we need to move L to the right. So while counts.size is greater than or equal to 3, or rather greater than 2, because that's the condition for invalid. Counts fruits L minus minus. We can cache this. Should we do that? Should we cache it? I guess we can do that. So we decrement it, and if that is now equal to 0, that way we access it only once. I guess that's better. I'm not really sure. From a stylistic perspective, I don't really know. Well, you can go either way. You can just like decrement it here and then do the if here, but I don't think it really matters. So if once we decrement it, it's now equal to 0. So if it's no longer in the range, then we don't need this, but it's just an extra check. So if this is 0, then counts.erase fruits L as a key, since we don't need it anymore. And then plus L, since now L moves over. No matter what, we deleted that element. Then once we do that, we know that we just did this whole while loop, so we know that our current range is valid. So our range is, let's see, it's inclusive of L and R. So the size of the range is equal to R minus L plus 1. So for example, if L and R were here, then we would have a range of size 1. L and R were here, then we would have a range of size 3. So we need to add 1. Range R minus L plus 1. Okay. Now let's see. We can just run it on the sample tests. Why did that not? Fruits.length. Fruits.size. I'm running on the sample tests. Okay. Can test some other edge cases, like for example, empty array should work for that, because then it's like it's always 0. I don't think there's any other edge case really, because yeah. Oh, okay, so it can't even be empty. Nice. Yeah, so I think... Oh. 0, 1, 2, right? Because it's 0 indexed. I believe that is all. Nice. Okay, so some things we can do. I would imagine unordered map is a bit slow. We can replace it with a vector where we sort of maintain the map ourselves. And I think it'd be faster since it's only 3 elements total. We could also... we could do some other stuff, I think. But the basic idea is 2 pointers, I think. That's pretty much the best we can do. Okay, sure. Okay, so the question itself went pretty smoothly, but honestly, you're probably expecting that. I would say my explanation was a bit disorganized, but honestly, I'm not sure, so you can be the judge on that one. And as for the code itself, I didn't feel like there was any real appropriate place to put comments, since the only sections of the code were the initializations and the main logic. But looking back on it though, I realized I could have put some comments on the core parts of the logic, so maybe that's a thing I could do in the future. Up to you to decide. And I tried to use fairly clear variable names. You can make an argument that I should have used left and right instead of L and R for names, but honestly I think it can go either way. It's mostly just a stylistic choice. I think L and R are clear enough for what they represent. But other than that, if you see anything else that's worth pointing out, feel free to. That's all from me though. Let's get into the next question. Alright, here we go. We have minimum domino rotations for equal row. So in a row of dominoes, like so. Okay, tops I and bottoms I represent the top and bottom halves of the ith domino. Domino is a tile with 2 numbers from 1 to 6, one in each half of the tile. We may rotate the ith domino so top and bottom swap values. Return the minimum number of rotations, so all the values in tops are the same, or all the values in bottoms are the same. Okay. 2e4. Okay, so immediately thoughts are there are only 6 values, so 1 to 6, which is a really small number. So that's worth noting, because what if we just so the thing that matters here is it's not really whether we have tops or bottoms be the value. It's more which value will be the one that's the same. Which value is the chosen one? So how do we figure that out? How do we... Okay, well, I know how to figure it out, but how do we figure it out smoothly? Like, how do we not write a mess of code? So we can keep track of which value is the chosen one. So each domino has 2 values, top and bottom. And these are only 2 values. So whichever values are not on a domino, so let's say for example top is 2 and bottom is 5, then that means that 1 cannot be the chosen one. Let's just write all these out. So let's say 1, 2, 3, 4, 5, 6 are our candidate values. So immediately 1 cannot be the chosen one, because how could it? Because we need either every top or every bottom to have 1 on it, but because 1 isn't even on this domino, that's just not possible. So 1 can't be the chosen one, and similarly 3, 4, and 6 can't be the chosen one. So that immediately, after inspecting only a single domino, leaves only 2 options. So we have 2, so just looking at the first domino, we have 2 possible options for that. So I think that's the best we can do, because we can look at every domino and we can prune it the same way. For example, if there's only 2 here, then we can rule out 5, and that would work, but I feel like that just wastes time, because this will be like, actually, it'll be like an extra O(n) sweep that might save us an O(n) sweep. I don't know if it's worth it. I mean, we could. Like, because this is an array of size 6, it'd be really good in the cache. Like, we could... Well, actually, this would be 6n. Yeah. This would be, like, 6n time. If we sweep through every domino, and for every domino we rule out the values that aren't on the domino, then that would take about 6n. Or it'd really take about 2n, but, like... I don't think it'd be worth it. So we look at the first domino, and we rule out the values that aren't on that first domino. So now the only values that we're going to try are 2 and 5. Oh, actually, I didn't even realize, but that's the same as this. Nice. So 2 and 5, right. So now we have to try 2. So let's say we have some dominoes. I can't draw. Sorry about that. This is horrendous. Okay, but now what we need to do is we want to do like a single sweep. So we sweep through all the dominoes, and we want to see if 2, this is, I'll just write this, first domino. So we try 2. So if 2's on the top, then that means that there's 1 less swap we have to do for the top. If 2 is not on the bottom, then it means we have 0 for the bottom. So let's say, for example, 5. Let's say now we have like 1 and 2. Is this the same? Wow. I'm like, okay. I'm like mentally internalizing the sample case. I'm not even like realizing that these are correct. So if we have 1 and 2, then now we have 1 less swap to do on the bottom. Or rather, we can keep track of it the opposite way. We can say, if we have 2 up top, well, actually, no. I think it's better. Yeah. Because if we have 2 both cases, then it's just easier to say, like, it's easier to count the 2's on the top than to count the number of swaps we have to do, since counting the 2's is really simple. So ultimately, the number of swaps we have to do on the top is like n minus the number of 2's on the top. And the number of 2's we have to do on the bottom is also n minus the number of 2's on the bottom. So we can count the 2's here, and we can count the 2's here. And if there's any domino that does not have a 2 at all, then 2 is invalid. And I think that's just it. So we look at the first domino, we try the 2 values there, and then can dominoes be empty? Tops.length is at least 2. So we look at the first domino, we try the 2 values on that. To try a value, we count the number of 2's on the top and the bottom, and then the answer is the minimum of these 2. So it's just whichever one of these is cheaper. I think that would just work. Yeah. So overall, just straight O(n), very clean. O(n) time, O(n) memory. I don't think we can do better. So let's see. Let's start with this. So int answer is equal to n plus 1. So n plus 1 represents no answer yet. Then at the end, we can say if answer is equal to n plus 1, then we have no answer at all. And then return answer. And then in this main loop, we will process the values, and we will just see if it's n plus 1 still. So for int value is equal to 1. So this is the domino value that we're checking. Then so we want to make sure it's on the first domino. So if value is equal to tops 0, or value is equal to bottoms 0. If it's on the first domino, then, so if it's on the first domino, what we're going to do is check it. So now we need to check. So int top count is equal to 0, bottom count is equal to 0, and valid represents if there's not a 2 on one of these dominoes, then, like for example, if this wasn't a 2, if this was just a 6, then ultimately we need to mark it as impossible. So that's what valid represents. So for int, what do? We just do I. Domino is equal to 0. Domino is less than tops.size. Domino plus plus. If what do we do? If tops domino is equal to value top count plus plus, if bottoms domino is equal to value bottom count plus plus, so we're just keeping count, and then this should all make sense. And then if neither of them are equal, then what we need to do is valid is equal to false. And then after we process that, if valid, then answer is equal to min of itself. And again, we use these formulas, so n minus top count, because that's the number of swaps we need to do. That's the number of dominoes that aren't already on the top, the number of like 2s that aren't already on the top, so the number of swaps we need to do, and also n minus bottom count, because both of them are possibilities. So let's see, that should get 2, or a compilation error. Yeah. I'm just gonna... Sorry, this is like muscle memory. I don't usually... It's because I do too much competitive programming. Usually you get the number n, like you usually get the number as input as well. So I would just normally have the value n to work with. So that's just sort of something I'm stuck with. So yeah, we should get invalid. Let's try inverting the array to make sure that we get both top and bottom correct. So we just swap the top and bottom for that. It should still get 2. And it should, because they're symmetric. So we shouldn't have an issue with that in the code. Let's test, make sure we get... Make sure we can correctly detect the answer of 0. Okay. I think that's it. Because it's up to 6, there's not really much more we can do. We're iterating from 1 to 6. We're checking that correctly. We are counting the top and the bottom, and if neither of them are valid, then we make valid false. If valid, yeah. Okay, seems legit. Alright, honestly, I think I did a better job on this one. I did comment for my n+1 convention and stuff like that, but honestly, I also think the live commentary I'm giving would substitute for comments and probably allow a hypothetical interviewer to understand me. And hopefully stuff like variable names is also fine, except for maybe the usage of n, but again, that's muscle memory that I'll just have to work on avoiding in the future. And the question went smooth once again, though I think this one was a bit more interesting than the previous. It wasn't just apply 2 pointers and done. There was a bit of like actual original logic you have to do for it. But either way, I think I'll do a hard difficulty for the next one just for fun. So that's all. Let's do that hard difficulty. Alright, so we have a hard one this time because why not? And this is smallest good base. Already we can see it has a great like to dislike ratio, so this should be fun. Alright, so you're given an integer n represented as a string. N can be up to 10 to the 18th. Why are you a string then? we call k is greater than or equal to a good base of n if all digits of n base k are 1s. Okay, so immediately, if k is a good base of n, then n is equal to 1 plus k squared plus k cubed plus dot 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 plus k to the x for some x. And the thing is, for most bases, x is going to be really small. In particular, so for most bases, x will be very small, right? So what that means is, let's say k is 1. No, k can't be 1, obviously. So let's say k is 2. Then, because n is at most 10 to the 18th, k is less than or equal to 60. Because 2 to the 60 is like bigger than 10 to the 18th. Let's say k is equal to, or sorry, this should be x. X is less than or equal to 60. K is equal to 3. It's like 40 or something. Yeah. So x is less than or equal to 40. So what we can do is we can try iterating over x. And if we iterate over x, then what we can do is we need to find n. We need to find k such that this, right? Why is this a string? I don't understand. Why is this a string? Because it's up to 10 to the 18th, which means we can store it in a long. So to find k, well, we can notice that this function of x, if this is a function of x and k, then with x constant, it's a function of k. And the function of k will increase like dramatically as we increase k. So what we can do is we can binary search over this, because we know n's going to be like some point here, if at all. So we can do binary search and we can find the value of k that satisfies this equation, and that will work. Okay, so the question is, I think probably the easiest way to do this is in Python. So I'm just going to do that. But why is it a string? Like why is it a string? Because that just makes things kind of annoying. But yeah, to avoid overflow, Python is a good move. So we iterate over x. X can be at most 60. So, or 2 to 60. No, 1. Yeah, it's definitely 1. And then find k, so we can binary search to find k. And then is there anything else we have to do? I think that's it, right? Binary search on k, see if it's equal to n. We want x to be as large as possible, so the first match we find, so as x goes up, k goes down. Which means that since we want the smallest good base, we want the largest value of x. So we iterate from x to, yeah. So for I in range 61, -1. I don't actually know how Python works, so I'm just gonna make sure this is actually doing what I want. I'm gonna go from 5 to, okay, so this should be down to 0. So that's just a little test, make sure that this indeed goes down to 1, and there we go. So now we iterate from, okay, so let's use power, I guess. So we can binary search on k. So k can be up to, okay, we can estimate the upper bound on k based on logs, but should we do that? Because I think that kind of defeats the point. I think that just wastes a lot of time. We might as well just do this. Yeah, okay. So k can be up to 2, So k can be up to 2, or as low as 2. Left is equal to 2. Right is equal to n. This is how I do my binary search. Left inclusive, right exclusive. So left equals 2, right is equal to n. Right. So while left is less than right, mid is equal to left plus right, floor divided by 2. So this is our estimate for k. Mid is our estimate for k. So then we check mid, k, mid. So what are we gonna check? We're gonna check what we need the power, we need the k, and we need the n. Do a documentation. 1 if yeah. Right, so sum is equal to 0 for I in range power plus 1. So that will compute that, and if sum is greater than n, return 1, if sum is less than n, this is C++ stuff. If sum is less than n, return -1, else return 0. So that will be our compare. I guess compare k is a better name. Sure. So if compare result is equal to 1, then that means our power is too big, so we need to do right is equal to mid. Elif, I'm inconsistent with this. Elif compare result is equal to -1, then again that means our value of k is too small. Also power mid n. So if our compare result is this, then our power is too small. So we need to do left is equal to mid plus 1. Else we found our answer. This is the smallest good base. So return, what is it? Return mid. And that should just work. No, stir mid. What do you mean unit code? Oh, int n. Yep. Let's just do that. I'm not actually. How do you use classes in Python? Is it this? Ugh, okay. Self. Is this how you do it? I'm not the best at Python. Okay. Let's see if that works. It should. Let's test 3, I guess. And does not contain any leading zeros. Alright, so we iterate over the power from 60 to 0. Let's do 2 to the 60th minus 1. 2 to the 59th. I want to test the biggest case. We should not have overflow issues, but still. The answer for this should be 2. And it works, yep. Okay, so we do binary search. While left is less than right, mid is that. We do the compare result. If it's 1, our estimate is too big, so we make the estimate smaller. If it's -1, our estimate's too small, otherwise it works. And this will always be reached because m-1 is an answer. So no matter what, we will eventually hit this return statement, even if it may not necessarily look like it. Yeah, that should work. Okay, this one wasn't that bad. I made the choice to do it in Python because I knew the handling overflow in C++ would be a fairly big pain, and I just kind of didn't want to. But then I also forgot how to use classes in Python, which may have hurt me a bit, especially in like a real interview. And the question itself was pretty smooth though. I think that the bad like-to-dislike ratio on the question was probably just because of overflow. And I think you can save a bit of time by doing some extra math to avoid the binary search, so maybe what I did was suboptimal, but whatever. It was pretty quick, so I would have had time to improve the solution in a real interview. And I think style-wise, wrapping the comparison in a function was unnecessary. I thought that I would be using it more than once, but later on I realized that I only called it a single time, so putting it in a function didn't really do anything. I could have just inlined it and put it right there. But otherwise, I thought everything else was fine. So, on to the conclusion. So ultimately, it's up to you to decide how well I did. As promised, I did treat it like an interview by sharing my thoughts and making attempts to have a cleaner coding style, but I'm not sure how, good it was. The time per question was very good, especially considering that I was taking it pretty slow, so I have no complaints about that. I would say that none of the questions were particularly complex though, so maybe I just got lucky with the simplicity of the ones I chose. So now it's up to you to answer. How much did competitive programming carry me here? I know it carried me through being able to find the solutions, but did it drag me down in the other aspects? Although I do have over a year of experience at just talking at a screen just like this while solving problems, so hopefully my explanation of my solutions was good since it's exactly what I've been doing for a while. But I don't know about the other things like style. And I'll give the same advice that I usually do. If you're wondering what to do for yourself, I would just say to take the common sense approach. Practice what you're trying to get good at. If your sole goal is to get good at coding interviews, practice coding interviews. Don't waste time doing something else that's only marginally related, like competitive programming. Especially because there are many aspects of coding interviews that aren't covered by competitive programming, like style, and sometimes are even the opposite of what competitive programming will teach you to do, because you're trying to go fast, like style choices. But yeah, that's really it. I'm interested in hearing the roast you guys have for me. But other than that, that's all. Goodbye.